These algorithms are for computing shortest paths in graphs. Shortest paths in graphs. We have a graph. We are given a graph. This graph is a weighted graph. There are some weighted edges. For example, suppose the edges have these weights, and then we are going to compute the shortest path between vertices. For example, we are going to compute the shortest path between node 1 and node 6. There are some paths between any two vertices, any pairs of vertices. We are going to compute the path that has the minimum weight, the path whose sum of the weights of its edges is minimum. For example, in this sample, we can go from node 1 to node 6 in this way, from node 1 to node 3, then to node 5, then to node 6. In this path, we have a weight 3 for edge 1, 3, a weight 2 for edge 3, 5, and for edge 5, 6, we have edge 4. So 3 plus 2 plus 4 becomes 9. The weight of this path is 9 because the sum of the weights of the edges in this path is equal to 9. There are other passes from node 1 to node 6. For example, if we are going go from node 1 to node 2, then node 4, then node 6, in this path we have weight 1 and another weight 1, and then weight 3. The sum of the weights becomes 5. So this path is shorter than the other path. In the first pass, the weight of the pass was 9. In this pass, the weight is 5, so it is better and it is shorter than the other. We are going to find the shortest one, the shortest path, the path that has the minimum weight. Okay, there are some algorithms. We talk about two algorithms, Dijkstra algorithm and Floyd algorithm. First, let's talk about Dijkstra algorithm. The sound is clear or not?
Yes, doctor. Very clear.
Okay.
Yes, doctor, it's clear.
Okay. One of the student asks about the exam. We teach 4 weeks or a month. Okay, we have 4 weeks for lecture and teaching. Then after that, you have 1 week. You have 1 week for studying the course. After that, you take the exam. Okay, so you have 1 week. You have 1 week time for study what has taught in the course. Okay. Uh, during these times, you should review the course, review the lectures, and if there is any problem or any question, you should follow that. Uh, that if you have any question, you can ask me, or you can ask the TA, and you should make yourself ready for the exam. It was on 6th of Bahman, as you know. Okay. I'm going to explain Dijkstra algorithms. I use a simple example to describe the algorithm. Suppose you have this graph age 1, 2, 3, and 4. Um, suppose the weights of the ages is something like this. Okay. In Dijkstra algorithm, we are going to compute shortest paths from one node to the others. Computing all the shortest paths from one given vertex to the others. Suppose the given vertex here is vertex 1. We are going to compute the shortest path from vertex 1 to the others. So we say this is the start vertex. From this vertex, we are going to compute the shortest path to the other vertices. We are going to compute shortest path between 1 and 2, 1 and 3, and 1 and 4. Okay. At the first step, we consider linear array, one-dimensional array that has 4 rooms. The number of rooms of the array is equal to the number of vertices. We have 4 vertices, so the array has 4 rooms. The node 1 is the start vertex, so we do not we have nothing in the room 1 because we do not compute the shortest path from node 1 to itself. For the others, we initialize the array by the weights of the ages. Node 1 to node 2, the age 1, 2 has the weight 1, so we put 1 here. Node 1 to node 3 does not have any ages, does not have any age. We do not have any age between node 1 and node 3, so we put infinity here for the weight of the age between 1 and 3, because we do not have any age between 1 and 3, so we put the weight of this age uh, as infinity. Uh, the weight of age 1 4 is 4, so we put 4 here. So we initialize the array D by the weights of the edges. If there is not any edge between the start vertex and an edge, we put infinity. Uh, okay, so we continue as I described. Uh, in this array, we find the minimum value. We have value 1, infinity, and 4. Between these three values, the minimum one is value 1. Okay, so we select the minimum value. Uh, because the value of room 2 is the minimum, we define W, vertex W will be equal to vertex 2, because the vertex W is the vertex that has the minimum value. Okay, here because vertex 2 has the minimum value 1, so we set W to a vertex 2. So W is the vertex that has the minimum value. Here vertex 2 is W. Now we consider the neighbors of W, the neighbors of vertex W, and check and check and check if we can update the weights of its neighbor. The neighbors of W are node 3, node 4, and node 1. Node 1 is the start vertex, so we do not consider it. The other neighbors of node W is node number 3 and number 4. We check if we can update the value of these uh, neighbors of W using W. I describe it in the next slide. Uh, we have node 1 as a start vertex. We have a vertex W whose value is the minimum. W has some neighbors. For example, suppose node V is one of the neighbor of W. We have a pass from a start vertex directly to V, and there is another pass from a start vertex to W, then from W to V. Okay. The length of path from vertex 1 to W is in dW. The length of path between a start vertex and V is dV, is stored in dV. And node W has an edge to node V that has a weight. We can show the weight of node W and V by, for example, CWV. uh, is the weight of H WV. We compare these two choices. We have two choices. You have a path from start vertex to V, which has weight dw, or its length is dw. There is another choice. We can go from start vertex to vertex w, and from w to V. So we compare these two, dv and dw plus cwv, and compute the minimum value between these two values. And dv, new dv is set to this value, is set to the minimum value between these two values. New dv, and this is the old dv. So we compare these two choices. One choice is we have the previous one, which we have found until now, a path from start vertex to V. The other choice is we go from start vertex to node W, then from node W to node V. We compare these two values and compute the minimum one, and update the value of the dv by this minimum value. So in our example, W here is node 2, has two neighbor 4, neighbor 3. The weight, the old value of D3 is infinity. The other option for node 3 is that we go from start vertex to W, then from W to node 3, which has weight 1 plus 3, which is equal to 4. 4 is less than infinity, so the weight of 3 is updated to 4. I write it here. D3, W here is node 2. D3 is equal to minimum between D3, old D3, new D3. Old D3 and D2, DW plus C2 to 3. The old value of D3 is infinity. The value of D2 is 1 in the array. In the array D, D2 is 1. And the weight of age 2, 3 is 3. So we have 3 here. The first value is infinity. The second value is 4. The minimum is 4. So node W helps to node 3 and makes it its path shorter. Now let's to consider the other neighbor of W, node W. The other neighbor of node W is node 4. In this graph, 3 and 4 are the neighbors of W. We try to update their the length of their passes using node W. The old value of D4 is 4. But if we go to W and from W to 4, we have a weight 1 plus another weight which is 1. 1 plus 1 is 2. 2 is shorter than 4, so the value of D is updated to 2. D4 new is minimum of D4 old and DW or D2 plus the weight of age 2 and 4. D4, the old value of D4 is 4. DW, D2 is 1. The weight of age between 2 and 4 is 1. So the minimum value is 2. And the value of 4 is updated to 2. So the new values in the array is like this. 1, 2, 3, 4. Start vertex does not matter. Node 2 has weight 1. 3 and 4 are updated, was updated. 3, the new value of 3 is 4 and the new value of 4 is 2. 4 and 2. Okay, node 1 was a start vertex. Node 2 in the previous step was W. We do not consider a start vertex, and the vertices that were W in the previous steps. Okay, so we do not consider node 1 and node 2, and at this step we just between the other nodes compute the minimum value. We have here node 3 and node 4. Between these nodes we again compute the minimum value. We have value 4 and value 2. The minimum value between these two values is 2. So node 4 will be the new W. In this step, in this step, W is node 4 because its value is minimum. We do not consider node 2 because node 2 in the previous step was W. In this step, we do not consider the nodes that were W in the previous steps. Okay, so between nodes 3 and 4, we just find the minimum. The minimum value is 2, which is for nodes for node 4. So W is set to 4. We have W equals to 4. Now we try to update the neighbors of W. Node 4, which nodes are the neighbor of node 4? In the graph, Node 4 has 3 neighbors. One neighbor is node 1, which is the start vertex. We do not consider it. The other neighbor of node 4 is node 2, which was the previous W. We do not consider it. Only one vertex has the neighbor of node 4 that is not a start vertex and was not previously W. So we just consider node 3. We check if the value of 3 can be updated using node 4. So D3, new value of D3 will be minimum of old value of D3 and dW, which is 4, plus the weight of age 4 to node 3. So we should compute the minimum between the old value of 3 is 4. D4 is 2 plus the weight of age 4, 3 in the graph. For age 4, 3 has weight 1. So we have 1 here. One value is 4, the other value is 3, the minimum is 3. So the weight of node 3 is updated using node W, which is 4 at this step. So the last D, the final values in D is as I write them here. Node 2 has value 1, node 3 has value 3, and node 4 has value 2. Okay, so the length of shortest passes is the values that are in this array, final values. Because why this step is the final step, because node 1 was a start vertex, node 2 has been selected as W in the previous step, node 4 is also selected as W in the previous step. Only one node has been remained. At this step we finish the algorithm because there is not any more nodes that can be selected as W, and there is no neighbors for W that we can update because only one node is remained here. So we stop the algorithm. These values are the final values, and this means that the shortest path from node 1 to node 3 is 1. The shortest path from node 1 to node 3 is 3. And the length of the shortest path from node 1 to node 4 is 2. So these values are the length of the shortest paths from node 1 to the other nodes, to node 2, node 3, and node 4. Okay, any question?
Good afternoon, doctor.
If there is any question or there is any ambiguity, I can explain again.
Excuse me, doctor.
Please.
Can we make these arrays in one table? Is that possible?
One table, yes, we can uh, show these steps in one table. Each uh, uh, each uh, each of this step
Each
in
move.
one row. Okay,
Each
the
move is
first,
one. Yeah, okay.
each of them in one row. The initialization is the first row, then the next the is the second row, and the final is the third row. We can show all of them in one table. Okay,
Thank you, doctor.
if you can, I can. If you want, I can explain again. What is the question method that come in the exam? The official question about this subject. Um, for example, you may given a graph, okay? Then um you will ask what's the shortest path, what's the length of shortest path, compute the length of shortest passes using Dijkstra algorithm. So you should run Dijkstra algorithm on the given example and compute the length of shortest path. Is it okay? Um, what about the shortest path itself? Um, in in the array, we have the length of shortest passes. If we want to find short, if we want to find the shortest path itself, how we can find it? Yes, I re-explain. Yes, no problem. I re-explain. Um, uh, the questions in the exam is similar to the questions in your exams. Okay, in your exercises, uh, and are similar to what I teach and the examples that I uh, run the algorithms on them. So uh, you can uh, you can find how the exam will be. Okay, please let me explain again this example. We are given a graph. Here has four nodes, four vertices. So we draw a linear array. We draw a one-dimensional array that has four rooms. One of the vertices is the start vertex. We are going to compute the shortest path from a start vertex to the others. Suppose node 1 is the start vertex. Any of the vertices may be the start vertex. Here, suppose node 1 is the start vertex. So we are not interested in the length of shortest path from node 1 to itself. So the value of room 1 does not matter. It's not important. The other values are initialized by the weight of the edge between a start vertex and that vertex. For example, room 2 should be the weight of edge 1, 2, which is 1. Room 3 is the weight of edge between 1 and 3. Because we do not have any edge between 1 and 3, between node 1 and 3, we can assume there is an edge with the infinity weight. If there is not any edge between two nodes, between a start vertex and a node, we put infinity in the initialization step in that room. For node 4, we have an edge between start vertex 1 and node 4, which has weight 4. So we put 4 here because the weight of edge is 4. This is the initialization. This is the initialization step, and these values are the initial values of the shortest path. Then we try to improve the length of shortest paths using some nodes. Okay. At the first step, we find the minimum value between these values. The minimum value in the array is 1. Okay, this is related to node 2. Okay, so we set w to 2. We set w to 2. W is equal to 2 because the value of node 2 is the minimum, which is 1. Okay, the value is the value is 1. The value of node 2 is 1, and this is the minimum. Now we try to update the neighbors of W. W has some neighbors. We check if we can make the length of shortest passes of the neighbors of W shorter. We try to make the length of shortest passes of the neighbors of W shorter. W, which is node 2 here, has 3 neighbors, node 1, node 4, and node 3. Node 1 is the start vertex. We do not consider it. 2 other nodes, 3 and 4, are the neighbors of W. We try to update the weights of nodes 3 and 4. For any neighbor v of W, we compare two values and we compare two options. One option is the previous pass and the previous value of v. I mean the v old. And the other option or the other choice is we use a pass from start vertex to W and from W to V. This is the other choice. We compare these two options and check if which one is shorter. We take minimum between these two options. Between dv, the old value of dv and the value of dw plus the weight of the edge between w and v. So for w, w, which is node 2 here, we have two neighbors for node w. Node 3 and node 4 are neighbors of w. We compare these two options for these neighbors of w. So we compute minimum of the old value of d3 and the value that we and the length of path from a start vertex to w, which is 2, plus the weight of the edge between 2 and 3. The old value of 3 in the array is infinity. Okay, so we put infinity here. The value of d2 in the array is 1, and the weight of edge to node 3 is 3. The weight is 3. So here we have 1 for D2 and 3 for the weight of age 2, 3. The minimum value between infinity and value 4 is value 4. So the new value of D3 is 4 at this step. The other neighbor is node 4. For node 4, the old value is 4. The value of D2 is 1. The value of the weight of age 2, 4 is 1. 1 plus 1 is 2. So we compare value 4 and value 2 and take minimum. The minimum value is 2. So the new value of D4 is 2 at this step. Okay. We update the array. The new value of D3 is 4. The new value of D4 is 2. Okay. So we continue. We have a start vertex. We do not consider it. We have node 2, which was W in the previous step. We do not consider it here. We just have 2 other nodes, node 3 and node 4. In this step, we find the minimum value between these 2 nodes. The value of node 3 is 4. The value of node 4 is 2. The minimum value is 2. Okay, this is the minimum value. Because value 2 is minimum and this is the value of node 4, so we select node 4 as new W, or new W is node 4. So we set W to 4. Again, we consider the neighbors of W. If we see the given graph, node 4, which is W at this moment, has 3 neighbors. One neighbor is a start vertex. We do not consider it. One other neighbor is node 2, which was W in the previous step, so we do not consider it. So there is only one neighbor of node 4, which was not, which is not a start vertex and which was not W in the previous steps. So we should try to update node 3 as the neighbor of node 4. W is 4, the neighbor of node 4 is 3. We try to update the value of 3. So we take minimum between the old value of 3 and the length of the path from start vertex to node W to node 4 plus the weight of age 4 to 3. The old value of 3 is 4. The value of node 4, or the length of the shortest path from the start vertex to node 4, is 2. So we put 2 here. The weight of the age between node 4 and node 3 is 1. 2 plus 1 is 3. We take minimum between 4 and 3, which is 3. Okay, so the new value of node 3 will be 3, which is shorter than the previous value, which was 4. So we update the value of node 3. The value of node 3 is at this step 3. Okay, we have node 1 as the start vertex. Node 2 was W in the previous steps. Node 4 was W in the previous step. Only node 3 is remained. When only one node is remained, the algorithm finishes and we have the length of shortest passes in the array. The final values are the length of the shortest path from the start vertex to any other vertex. Okay. Okay. Let's talk about Floyd algorithm. Floyd algorithm is another algorithm for computing shortest paths. The Dijkstra algorithm computes shortest path from one vertex to the others. Okay, it is called single source. Single source. Single source. From a start vertex, from a start vertex to the other vertex. This is the single source. Single source. Um, but in Floyd algorithm, we compute the shortest path between all pairs, any two pairs, any two vertices, all pairs. For any two vertices, we compute the shortest path between them. So this is all pairs. This is an all pairs algorithm. Okay, let me explain the algorithm by a small example again. Suppose we have this graph. Suppose the graph is the previous one. Okay. 1 1 3 4. Okay. At first we at steps 0 we consider the adjacency matrix of this graph. This graph has 4 vertices, so its adjacency matrix is 4 multiplied by 4 matrix. I mean there is 4 rows and there are 4 rows and there are 4 columns. 1 2 3 4 1 2 3 4. We put 0 on the main axis, on the main axis of the matrix. I mean room 1 1 2 2 3 3 and 4 4 are 0 because we are not interested to a pass from 1 to 1 or from a vertex to itself, so we put 0 here. Then the other rooms of the adjacency matrix is fooled by the weights of the edges. Adjacency matrix. The weight of node 1 2 is 1 1 3 one tree, or the previous graph was node 3 was there and node 4 here. So let me update the picture. This is node 4 and this is node 3. Okay. The row 1 and column 3, in row 1 and column 3 we put infinity because there is no edge between node 1 and node 3. For edge 1 4 we put 4 here because the weight of this edge is 4. The weight of node 2 1 is 1. Node the edge 2 3 the edge 2 3 is 3. The edge 2 4 is 1. The weight of edge 2 4 is 1. 3 1 is infinity again because there is no edge between 1 and 3. 3 2 is 3. The weight is 3. 3 4 is 1. 4 1 is 4. 4 2 is 1. And 4 3 is 1. This is the adjacency matrix. In the first step, in the initialization step, we consider adjacency matrix. Then we try to improve the values. We try to make the values less and less until we reach to the shortest paths. Yes, we put the value, we put 0 on the diameter because we are not interested in a path from 1 to 1 or from 2 to 2. Okay, we just want to compute the shortest passes from a vertex to the others, not from that vertex to itself. So we are not interested in the values on the diameter. We put 0 on the diameter. Then in the next step, we try to improve the values. How we can improve the values? Suppose from node I to node J, we already have a shortest path until now. At this step, until now, we have computed the length of the shortest path between node I and node J. In this step, we want to check if vertex K can help to make the path between I and J shorter. So we have two options or two choices. The one choice is the previous path that has been computed between I and J until now. And the other option is to consider node K as an intermediate vertex in the path between I and J. I mean, we go from I to K and from K to J. This is another choice for a path between I and J. The path between I and K has a length which is stored in AIK in array A, in row I and column K. And the length of the path between K and J is in A, K, J. I mean in the row K and column J of matrix A. We compare these two options. A, I, J. The new value of A, I, J will be minimum of the old value of A, I, J, and the value A, I, K plus A, K, J. We compare these two values. Any of them which is smaller will be selected as the new value of Aij. Uh, uh, what's the vertex K? We let K be 1, 2 to the number of vertices from 1 to uh, the last vertex. I mean K in the first step K is 1, in the second step K is 2, then 3, 4, 5, until the last step K is the number of vertices or the last vertex. Okay. In our example, we have 4 vertices, so K in the first step is 1, in the second 2, in the third step is 3, and the fourth step is 4. We should compute uh, this formula for any ij for k from 1 to 4. If we consider k which is set to 1, for any ij we should compute aij as minimum of a old value of aij and ai1 plus a1j. So in the matrix if we consider row 1 and column 1, please note here aij is in the column 1. For any I, the column number is 1, and a1j is in the row number 1. For any j, we are in row number 1. So we are uh, we are adding a value in the uh, column number 1 with a value in the row number 1. The 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 value in the row I of column 1 is added to the value of column J of row 1. Okay, so we consider row 1 and column 1 and sum up and adds the value which are in this row and this column. Okay, for example, consider this this room in the row 2 and column 3. The value is 3. We should compare this value, which is 3. The old value of A23 is 3. And we should compare it with the other choice, which is to this value, which is in the room 2 1 in the row 2 column 1, and this value which is in row 1 column 3. If we add these two values 1 and infinity, we get infinity. The other choice is 3. The minimum value between infinity and 3 is 3, so this value does not change. This value is not changed and remain itself. Also for other values, here we have value 1. The value 4 plus value 1 is equal to 5, which is greater than 1, so this value is also is not changed. The value of other rooms also does not the other values in the other rooms are not changed because in this formula the old value of aij is less than the value of ai1 plus a1j, so a1 is same as a0 here. A1 is the adjacency matrix, which is updated using node number 1. A0 is the initial adjacency matrix. So A1 is as the A0 and does not change, and is not changed. One infinity 4, 1 infinity 4. Uh, 3 1 3 1 3 1 1 1. Okay. Now in the next step we set k to 2. K will be node number 2. We set k to node 2 and we use this formula to update aij. Aij equals to mean aij old value of aij and ai2 plus ai2 plus a2j. This means that we should consider column 2 and row 2. Column 2 and row 2. Row 2 is this one. Column 2 is this one. 1 2 3 4. 1 2 3 4. Then we try to update the values of the other rooms by using column 1, column 2, and row 2. We do not consider the diameter. Diameter is always 0. The value of room 1, 3, I mean row 1, column 3 is infinity. But the value of the of the column 2 in this row, in row 1, is 1, and the value of row 2 in this column is 3. The sum of 3 and 1 is 4. The old value is infinity. Between these two values, the minimum is 4. So we update infinity and set it to 4. Let me see. Let me write it. A 1 3, A 1 3. The new value of A13 is set to minimum of old value of A13, old value, and A12 plus A23, which is equal to minimum of the old value of A13 was infinity. The value of A12, the value of A12 is 1. The value of A23, the value of A23, row 2, column 3 is 3. The sum of them is 4. The minimum between infinity and 4 is 4. So the new value of A13 is 4 instead of infinity. So the array A2, which is the new adjacency matrix for in step 2 when k is 2, is like this. Diameter is 0. The room 1 3, which was infinity, is now 4. The room 1 4, I mean row 1 column 4, was 4 before. The old value was 4. The new value is the sum of 1 and 1. 1 and 1, sum of 1 and 1 is 2. So the old value 4 is updated and is replaced by 2. And also the other the value of other rooms. For example, we have value 1 here, but if we add value 1 and value 3, the sum will be 4. The old value is less, so we do not update the value of room 3 4. I mean the value of row 3 column 4, which is 1, is not updated because the old value is better than the other choice. So we have we have 1 3 1 1 3 1 1 3 1. Here the value will be 4. The value of here is 2. These values do not change. This 2 and this 4. Okay, now we go to the next step. In the next step, k is 3. And we should consider column 3 and row 3. Row 3, column 3. The values of the other rooms is 1 1 1 2 1 2. No, none of these values can be make shorter by column 3 and row 3 because for example here we have value 1, but the sum of 3 and 1 is 4, which is not which cannot be shorter. Or we have value 2 here, but the sum of 4 and 1 is 5, which is not smaller than 2. So node 3 does not help to make the length of shortest passes shorter. So A3 does not differ from A2, and we have the previous matrix here for A3. I mean, node 3 does not help us to make shorter the length of passes. Okay. 1 4 2 1 4 2 and 3 1 3 1 3 1 and 1 1. Okay. Then we go to the next and the last step. In the last step, we consider the node 4. For node 4, we should consider the column 4 and the row 4. And we are trying to make the length of the passes shorter. Okay. Value of room 1 2 is 1. It does not it is not we cannot make it shorter using column 4 and row 4 because we have 2 here, value 2 here and value 1 here. The sum of the value 2 and 1 is 3, which is not less than 1. But we have a value 4 in row 1 column 3. We have value 4 here. The sum of value 2 and value 1 is 3, so we can make this value shorter, and 4 becomes 4 is replaced by 3. Also, we have value 3 here, but sum of value 1 and value 1 will be 2, which is shorter. So we replace value 3 by 2. So the final array will be like this. Uh, the value 4 is replaced by 3. The value 3 is replaced by 2. I have 2 here and 3 here. This is the final values. So we start by the adjacency matrix in the initial step, then using node number 1, 2, 3, 4, and so on until the last node. We try to make the values shorter and shorter, less and less, if it is possible. And we using this formula, we try to make the values less and the length of shortest paths shorter. Uh,
Excuse me, doctor.
Please,
Could you repeat A1?
A1, okay. Uh, at the first step, we have the adjacency matrix itself, okay? A0 is the same as adjacency matrix. And we put the weights of the edges in the rooms of matrix. When we do not have an edge, we put infinity instead of the weight. Then we are going to compute A1. Excuse me. Okay. For computing A1, we use this formula. K may be 1, 2, 3, or any vertex in the steps. So we try to compare two choices. The old value, the old path between I j is compared with the new path, which pass through node k. K in the first step is 1. So we consider node 1 as an intermediate node, and we consider the passes that pass through node 1. Let me go ahead. So for computing A1, we set K to 1 for any ij. Ij I can be 1, 2, 3, 4. J can be 1, 2, 3, 4. For any ij, we compute the value of ij. The new value of ij is computed by taking minimum between two values. The old value of aij, by old value of aij, I mean the value that was computed in the previous step. Here I mean a0 ij. Old value of aij is the value of aij, and that is computed until now. And we compare it with the sum of these two values. AI1 plus AI1 plus A1J. Um, the value of AI1 uh, is uh, uh, is in row one. Excuse me, is in column one, row I. So we consider column one. Uh, the value of A1 J is in row one. So we consider uh, row one, the first row and the first column. Okay. In the first column, we uh, consider the value that is in the first column and in the row I. And in the first row, we consider the value that is in the column J, and we add these two values. This means that when we want when we want to go from I to J, we can go from I to node 1, then from node 1 to node J. And node 1 is an intermediate node. Uh, because node 1 is an intermediate node, we add these two uh, value. Consider this picture. If node K is an intermediate node, we go from I to K and then from K to J. We compare this option with the old